My name is Alan Monaghan, and it is my pleasure to be your moderator for today's session. We have a webinar on Beyond Capture, CO₂ Mineralisation and Carbon Circularity for a Net Zero Industry, presented in cooperation between the Net Zero Industries mission and the Carbon Dioxide Removal mission, both part of Mission Innovation. As moderator today, it is my pleasure to introduce our speakers. Our first speaker today is going to give you a welcome. It is my pleasure to introduce Urban Piker. He's the Mission Director of the Net Zero Industries mission, representing our co-lead nation of Austria. Urban is currently the head of the Industry, Enterprise and Financing Department and Deputy General Manager of Austria's Climate and Energy Fund, and brings to the role extensive experience in industrial transformation, clean energy and financing. Take it away, please, Urban.
Thanks, Alan. Thanks for the kind introduction, and thanks for the role that you will take in the next 1.5 hours. It's my great pleasure to welcome you to today's webinar. It's, as Alan said, part of our Net Zero Industries Insight series. Thank you all for joining us from across the globe. Once again, it's a very international audience, and we are truly delighted to have you all here. Today, we will look into a very particular topic, CO₂ mineralization and carbon circularity. It's a topic that is unique, not just because the topic itself is truly fascinating, but because it's obviously a unique contribution to go the last mile towards reaching net zero. And what is particularly fascinating about this topic for me personally is that there are very few aspects of the industrial transformation that comprise such a broad variety of sciences and skills like CO₂ mineralization and carbon circularity. You need skills in geology, engineering, physics, chemistry, logistics, economics, material sciences, and I'm sure I forgot to mention a couple of other ones. So what I wanted to say is that you need to master quite a lot of skills to get a project on the ground, and I'm really curious and very much looking forward to the project presentations and, of course, to your questions. As Alan said, the webinar today is again a special one for another reason. We are co-hosting it with our sister mission, the Carbon Dioxide Removal Mission, which is part of the Mission Innovation family, and my fellow mission director Juho Lipponen will come right after me with his welcoming note. But before that, let me briefly allow me to introduce our mission, the Net Zero Industries mission, to you. So we are a global initiative under Mission Innovation, and we are dedicated to accelerating the transition to energy, the transition of energy-intensive industries such as steel, cement, chemicals, refining, and high-temperature heat. And obviously, these sectors are not just vital for our economies, but they account for approximately a quarter of global greenhouse gas emissions. And it is key to transform them to achieve our climate goals. Cutting emission in these sectors is especially demanding due to their complexity and the significant investments that are still required. And while many breakthrough technologies already exist, they still need to be scaled up and commercialized. And our goals, which you can see summarized here, are paying into this task. So our ambition is to deliver 50 large-scale demonstration projects across all these energy-intensive sectors, and to support the testing of a range of technological pathways. So we want to support the fast track of the development of these breakthrough low-emission technologies, reaching TIL6 in a speedier way, and at the same time contribute to reducing capital expenditure by 15%. One of the key reasons why we host these webinars is to share knowledge and to promote innovative solutions for the net zero transition. We believe that building trust in new technologies begins with understanding, and for that, knowledge is essential. And I'm, as I said, very much looking forward to the project presentations. And with that, I'd like to hand over to Alan Monaghan again, who will be so kind to moderate us through the next 1.5 hours. Please. Ellen.
Thank you, Irvin. Before we jump into the agenda fully, I'd like to invite our fellow mission director, Juho Lipponen from the CDR mission, to actually give a welcome introduction as well. Juho is the coordinator and the acting director of the Mission Innovation CDR mission. He works with the mission member countries to advance innovation and policy development of technological carbon dioxide removals. Prior to this, Juho was head of carbon capture and storage unit at the International Energy Agency and acting head of energy technology in the policy division. Juho, please, if I can pass to you.
Great, thank you so much. And just checking, Alan, can you note if I'm audible?
Absolutely.
Very good. Okay, so good morning, everybody. Good afternoon. So yeah, I'm Juho, coordinator and acting director of MICDR mission. And thanks indeed to our colleagues and sisters and brothers from the Net Zero Industries mission for collaborating on this event today. And Alan, thanks for leading us through today's proceedings. Everybody out there, thanks so much for your interest. It's really a pleasure to know that you all are there, even if we don't see everybody. And of course, thanks to all the speakers who prepared content for this session. So our mission, the MICDR carbon dioxide removal mission, as its name indicates, looks into and concerns itself with carbon dioxide removals. So an activity which is different from mere reduction or avoidance of emissions. And removals can be a solution for the net zero across many sectors in the economy. Obviously, particularly important for sectors and activities that are very hard to decarbonize, perhaps in some cases not possible or very expensive. And in that case, offsetting the remaining emissions through removals may simply make more economic sense. And I think that's how we link closely to Net Zero Industries missions, and it's really good to collaborate on this event today. Just a few words. I won't spend time on these. You see our member countries on the right-hand side of this mission. We've got 11 full members. We're co-led by Canada, Saudi Arabia, and the US. And then they are joined by a bunch of other active countries in removals. And what we do is to, first of all, to try to enhance the understanding of the CDR potential in different countries. Secondly, to advance R&D for these technologies. And thirdly, to foster global demonstrations and pilot scale tests. You don't need to remember this, but maybe this just gives a flavor on how we have organized our work. We have both technical tracks. Carbon mineralization is one of them, where we look specifically into mineralization technologies. We are co-led by Australia and Saudi Arabia, and we have speakers from both countries at this event, which is great. And we have a few other technical tracks as well. And then we have horizontal or cross-cutting activities that look into demo and pilot plans, CDR maps, engaging with the students in a smart CDR competition and so forth. So a kind of a matrix organization, if you like. And the final point I wanted to just make that our vision is to enable CDR technologies to achieve a net removal of 100 million tons per year globally by 2030. We all have these lighthouse figures, and I think they're important to focus attention and to drive things forward. But that's all I had to say. Thanks everybody for joining. Really great to have you here, and looking forward to the talks. Thank you.
Thank you, Juho. As moderator, it's my pleasure now to introduce our keynote speaker, Sophia Hamblin-Wang. Recognised as a World Economic Forum Young Global Leader and member of the Asia Society, Sophia is a graduate from Harvard University's Executive Education Program. Sophia is also currently the co-founder and Chief Operating Officer of MCI Carbon, who are delivering a novel carbon capture technology right here in Australia. Sophia, if I could pass over to you, welcome and thank you for speaking with us today.
Thank you very much, Alan. Can I just confirm everyone can see my slides?
That's perfect, yes.
Great. So thank you very much. I'm just acknowledging I'm coming to you from the lands of the Ngunnawal people in Australia, and pay my respects to elders past and present. I'm the co-founder and COO of MCI Carbon, as Alan just mentioned, and over the past 13 years, it's been my pleasure to be scaling mineral carbonation technology from lab into pilot into demonstration, and now embarking on the commercialization journey of carbon capture and utilization and CDR technology. I think one of the reasons why I'm speaking to you today as the keynote is because mineral carbonation itself and MCI Carbon, we are a business model. So at our heart, we specialize in making rocks and waste extra absorbent with CO₂, and then the output material from absorbing the CO₂ being extra useful in the built environment and in advanced manufacturing, so that ultimately downstream we have customers that want to buy the carbon embedded products and the resulting residues that are associated with that. So MCI, at our heart, we've been always founded upon the principle that we want to be locking away the maximum amount of CO₂ possible, but we want to be making money out of that process in the first place, because we think that that will incentivize the world to decarbonize in the fastest possible way. So MCI itself, we've received more than $40 million worth of government funding from the Australian government in order to get to where we are today, and raised around $50 million from global investors. And those investors are Orica, which is a mining services company, RHI Magnesita, a refractories company, Itochu, a Japanese trading house, Mizuho Bank, a Japanese bank, Sumitomo Mitsui Trust Bank, another Japanese bank, and Mitsubishi Ube Cement Corporation, which is a Japanese cement company. So we've grown so far using investment from strategic investors that have a key interest in decarbonizing global industries. And we have been really grateful to our investors who got us here so far. So MCI Carbon's technology, we're really driven by three main drivers. One, as I mentioned, is around the economical carbon abatement. So showing emitters that you can make money from decarbonizing. And that's the very first one. But also the rise in demand for carbon embodied materials. Now you see construction materials around the world do have a really high carbon footprint currently. And we see a changing tide in legislation and policy around the world, driving a higher demand for low carbon materials, and even more knowledge around what the carbon footprint is of each individual material that is used in the built environment. So we see that that demand rising, and we also see waste valorization as becoming way more important to our downstream customers. So this circular economy and having a zero waste business is increasingly important in the global landscape. We also, as you'll hear a lot today, mineral carbonation is a permanent and durable way to store CO₂. So we actually, in our industrial facility, create a magnesium carbonate powder and product, and we can really show and verify and validate with our customers and with governments that the CO₂ goes in and the carbonate comes out, and it's quite simple in many respects. And so we're able to work with our customers on showcasing that, and it's very strong. We produce some core products, magnesium carbonate, calcium carbonate, amorphous silica, and also some carbonated slag products. So the downstream products that we produce are dependent upon the input material, the feedstock material that we feed into our plant. But our core product markets are around these 5 product materials. We always start with that mineral feedstock, and that is usually a steel slag, bottom ash, other different types of ashes around the world, and mine tailings. And we process it with a source of CO₂. Now, MCI Carbon's technology is actually able to be integrated into raw flue gas and low and dilute streams of CO₂. We can go down to like a 5% or a 10% purity of CO₂ in our process, because we're actually a capture and a transformation technology in one step, and we produce two quite pure and separated downstream products. It is typically a magnesium carbonate and an amorphous silica, or a calcium carbonate and a silica product, depending on what product stream we're looking at. But absolutely happy to talk more about that if people have questions. This is a mock-up of what our technology really does, where we feed the industrial waste into our plant and combine the feedstock with the CO₂ source or pumped flue gas from the industrial site next door, which then produces the downstream output materials that get shipped or freighted in some way to the local markets. This is an extremely scalable technology. So we are, as we get to commercially viable stage, we are looking at a number of different plants around the world that have sizes from 50,000 tons of CO₂ processed per annum up to 2 million tons of CO₂ per annum at any one site. So we are an extremely scalable CCU and CDR technology solution, and we can actually integrate with obviously with direct air captured CO₂, which is one of the key reasons why we are a CDR technology as well, because a lot of direct air captured CO₂ needs somewhere to permanently and safely store that CO₂. And we think that we're in our industrial setting, we've got one of the best and most productive and profitable pathways to store direct air captured CO₂. We also have a whole geology aspect of what we do to do a global scan of the best ultramafic and industrial waste rocks around the world that are extra absorbent to CO₂. And we have geologists working within MCI to make sure that we have the best and top knowledge in the world in terms of safety, as well as the highest absorbent CO₂ and best use cases as well. So we have a global atlas that we use for that. We have a demonstration plant, a pilot plant that we've been running since 2016. And then we also have our Myrtle demonstration plant. And I'm really proud to say that our Myrtle demonstration is up and running now. It's a technology readiness level 7. It has a capacity of 2,500 tons of CO₂ per annum when operating at full capacity, and it will create around 10,000 tons of low carbon materials per annum. Now, the way we've built this is as the Swiss Army knife of mineral carbonation. So we actually do everything possible at this plant when it's at full capacity. So we can carbonate steel slags and ashes and different kinds of ultramafic rocks. We can process flue gas and direct air captured CO₂ and pure stream CO₂ that comes from an ammonia plant next door, and we can produce the variety of downstream materials that I've already mentioned. So the whole idea behind this plant is that it's a demonstration plant that is tailorable and tunable to the settings of our customers so that they can get the confidence and the techno-economic data that's necessary for them to build their first of a kind commercial plant on site next door to their facility. Now, we see this actually working in real life really well with our first customer. So with our RHI Magnesita, they are our first customer running a campaign at the Myrtle facility, and they will be building a 50 to 100,000 ton CO₂ per annum plant in Austria. And we are actually one of the beneficiaries of a net zero industry mission. I think it started a grant that started from the Net Zero Industry Mission, and it's a collaboration grant from the Australian government and the Austrian government to incentivize industrial decarbonisation collaborations between the two countries. And we, along with RHI Magnesita, applied for that grant, and we won $3.8 million from that. I'm wrapping up now, Alan. Just in terms of what makes MCI Carbon different, we have a very structured and data-driven methodology to only deploy at the best cases around the world. So we do our global mapping with our customer. We screen and do feedstock screening with them, and then we provide quite a lot of comfort around those economics. So as we scale over the next years towards a 2030 profitability time, we will be able to deploy rapidly and really help to achieve that 100 million tons by 2030 target that we're all working towards. So thank you very much for listening, and look forward to participating in the panel later.
Thank you so much, Sophia. It's always, I find it quite invigorating to see real boots on the ground in regards to making progress and demonstration of these technologies, and proudly Australian innovations and demonstration at work. Without further ado, please remember to add your questions to the chat, and we should be having a panel discussion with questions at the end, and all of our speakers will be hanging around to answer your questions. It is my pleasure, however, to move to our next speaker, and that is Professor Hussein Hotait. Hussein is a professor of the Earth Systems Science and Engineering program at KAOST. His work spans reservoir engineering, multi-phase fluid flow and reactive transport, with a present focus on energy transition applications. It's my pleasure to introduce you to Professor Hussein Hotait.
All right, thank you very much, Alan, and thank you for this opportunity. It's my pleasure to share with you today our recent work on the deployment of a pilot in Saudi Arabia. We call it GGZAN carbon mineralization pilot. So first, I will go very quickly through a quick background for those probably who are not familiar with this technology, and then I'll go, walk with you through the different stages that we sort of followed to from the very early time to the of actually planning for this pilot till the deployment, and also I'll share with you some of the key results related to that. Some people at this point, they still ask me if mineralization is true, right? Does this really happen and so on? I just want to remind everybody that actually this mineralization is part of our ecosystem. It is part of how our Mother Earth, calibrate itself, especially when it comes actually to the temperature and so on. So as actually rain, interacts with CO₂ in the atmosphere, CO₂ dissolves in water and forms a weak carbonic acid with pH about 5.6, and then when it interacts with reactive rocks like silicate rocks like basalts, ophiolites, and so on, it leaches some of the cations out, and with this what we call the natural weather, and these ions eventually end up in the sea. And as condition changes there, pH increases, you end up actually precipitating some of these cations like calcium. It combines with carbon and form calcium carbonate. And at some point, of course, over time, this gets buried. And when you get too deep and hot, eventually you're gonna get degassing through volcanoes and so on, and CO2 come back actually to the atmosphere. And this is what we call the carbonate silicate cycle. Of course, as the CO2 increases, concentration increases in the atmosphere, you are going to get increase in temperature, and this is sort of increases the process, you know, the dissolution and precipitation process that eventually actually lead up to higher, if like, entrapment of CO2 or removal of CO2 in the system, and you end up with cooling of the atmosphere. And this is how what we call the Earth thermostat. This is how our Mother Earth calibrates itself. Of course, this happens over geological time, right? Over millions of years. And of course, right now we're emitting too much CO2 for our Mother Earth to calibrate itself. Now, coming back to mineralization by itself, using rocks to entrap CO2, is this new idea? Actually, it is not. It has been proposed in the literature a long time ago. I just found this paper from Los Alamos talking about this from 95. Probably there are earlier papers on this, but they did the assessment in using silicate rocks, basalts, and so on, and even they did the assessment on how much actually you can entrap and energy needed and so on. So this is this in history. Now coming back to what we currently have regarding mainly focusing on basalts here. We have, of course, very good demonstrations out there, you know, pilots like the Wallula, for example, in the US, Carfix, and then the Jizan. This is mainly focused on basalts at, relatively speaking, larger scales. There's many others demonstration in different rock types, like ophiolite has been demonstrated on Oman, UAE, in Australia and Canada and other places around the world. Okay, for it. Now, all right, now coming back to Saudi, of course, this technology wouldn't apply everywhere, right? You need to you have the right resources in terms of reactive rock and so on. This is the map of Saudi Arabia, and I'm highlighting here, you see in the dark gray, these are volcanic formations. This is some footage of it. And this is what we call here Harras, or the hot fields, okay, for it. So just to get a scale, you know, feeling about the dimensions here, this is, for example, Harrat Rahat. It is about, dimension-wise, about 100 by 300 kilometers. So if one want to put, for example, a country like Lebanon, for example, this is almost half the size of one of these Harrat's fields, you know, for it, or volcanic fields. All right. Now, coming back to the pilot, as I mentioned, it took some effort, right, to do the planning from the initial assessment to the design, deployment, testing, all the way until actually the execution and monitoring. I'll walk through very quickly through the steps that we followed here. There has been a lot of field work, geology work to understand our resources and what is actually the properties of these basalts. We've been actually mainly focusing on basalts here, thickness, for example, presence of water in them, and so on. And of course, also fracture system, because it's critical for the injectivity of the fluids underground. And then there has been work on the characterizing these basalts, because some of them are recent, like few thousand, maybe 10,000 years old, versus older ones that are probably 20 million years old, and so on. And there is some level of alteration that already happened, meaning that some already have experienced natural carbonation in these basalts. So it was actually important to understand their chemistry and composition. And then it took all the way actually to select the location of the pilot, where we selected it based on different, critical criteria, like of course, the availability of the resources, like the basalt thick enough. We need to have, enough depth and thickness and presence of water in the system. And also you need to have it close to the point source, like in this case, it's close actually to industrial city, where we have the availability of CO2 there. And then, of course, a lot of work has been done in terms of once we have the location of the pilot, in actually understanding more, get more in depth in understanding the reactivity, for example, of these basalts, and then doing some modeling for scaling this up and so on, understanding the fracture system and so on. So, you know, as you probably know that, you know, we don't have here in Saudi Arabia luxury of what, for example, in Iceland, right, presence of water and so on. So the pilot here was selected to have the closed loop system where we, in this scenario, we have injected 2 wells, producer and injector. Water was actually produced from the producer and get recycled back to the other well injector where CO2 got mixed with this water and got injected underground. And this went through a closed system. So no make-up water coming from out the system. So back to the timeline of the pilot. Basically, this drilling started in 2022. And then after that, we did some initial assessment of the groundwater system to understand injectivity, productivity, understand also we use tracer here to assess the subsurface characteristics like presence of fractures, UL system, and so on. And then we went for CO2 injection. In the second stage, we injected about 130 tons over 2 months' time. And then after that, we went actually to the pilot monitoring stage where we monitored this for about a year. Now, quickly on this, based on the analysis we did using the tracers and then samples we got from the field, we showed that strong signal of mineralization of about 70% of that CO2 got mineralized within about a year or so. So I have quick here, this sort of word slide, I will share this material later if when I get to this in terms of the more details about the pilot and so on. I just have one last thing to just highlight some of our current work right now. We try to extend this technology from the subsurface or the in situ to the ex situ, and we're actually able to mineralize or accelerate the mineralization, by a very large factor. We're able to do this within a couple of hours, actually, in terms of the dissolution and precipitation. And besides that, we're able to extract other minerals and metals out of the basalts like aluminum and iron and so on, and silica. So with that, I just want to thank all our collaborators here, work on the pilot, big team here. And for more details, also, I shared with you the link of this paper so you can look in more details about it. And with that, Alan, I'll get back to you and happy to take any question by the panel session. Thank you.
Excellent. Thank you, Hussein. Fascinating, the achievements that are being made. Never ceases to amaze me. As I said, we will please put your questions in the chat. A question did come through. Yes, presentations will be shared on our website after the session, as will a recording of the webinar itself. Our next speaker, so questions in the chat, please, and we will put them at the Q&A panel session at the end. But before then, it is my pleasure to introduce you to Angeliki Kapatsa, a geologist from Carbfix. Angeliki leads geological screening and subsurface evaluation for safe, permanent CO2 storage and carbon mineralisation at sites worldwide. Her work spans geological modelling, reservoir characterisation and subsurface risk assessment. If I could, it is my pleasure. Please, Angeliki.
So hello to everyone. Good morning. Thank you so much for having me. It's actually very exciting to see the previous presentation. I see all this progress that has been made with several field demonstrations, and I'm just happy, of course, to be sharing with you here the scaling up activities that we have within Iceland and, of course, all around the globe. So yeah, just to reintroduce myself, hello everyone. My name is Angeliki Kapatsa. I'm a geologist. I'm based in Reykjavik at the moment. Basically, I'm working on subsurface characterization and CO2 mineral storage. And today I'll just taking some time to talk about Carbfix, and the focus, of course, is going to be mostly on our scaling up activities. So thank you so much for having me. Now, a little bit of an introductory, and of course, a couple of things that have been mentioned in the previous presentations. Now, Carbfix turns captured CO2 into stone. underground in less than 2 years through our proprietary technology that overall imitates and accelerates natural processes. And this is how we do it. CO2 is being captured and then it's being dissolved into water. And then this CO2 dissolved in water is being injected in basalt or other reactive rock formations, ultramafics, etc., etc. These reactive rock formations, they should have cations like calcium, magnesium, and iron. And overall, as we see, in less than 2 years, it's been proven that those metals, after they've been leached to, they turn into solid carbonate minerals, as we can see in this core, for example, in this slide. Now, despite challenges, it is important to keep in mind that we have a commercially ready technology that has been proven and certified. It is permanent, safe, cost-effective, and scalable. And here on the right-hand side, there is this nice picture of an announcement of the first third-party certified carbon removal credits through underground mineralization. And this was done by Puro Earth based on their strict high-quality methodology for geologically stored carbon. And this methodology was approved for the Orca and Mammoth capture facility with CO2 injection with Carbfix in Hellisheiði, which I will show you a little bit more information about it in the next slide, actually. Now, over here, I'll go you through a short journey on the scale-up that's been achieved in Iceland, and one site called Hellisheiði. A little bit more information on that later. Now, the very first industrial data capture and storage chain in the world is actually shown on the left-hand side, and I hope you can actually see my cursor. So on the left-hand side, you can see Mammoth. Mammoth currently, it's been operational since 2024 and can capture 36,000 tons of CO2 annually. But of course, it didn't actually start like that. Here you can see the first and second phase of this stack facility. It started in 2017 with Arctic Fox that was able to capture around 50 tons of CO2 in a year, just behind the power plant. And then, of course, the first commercial DAC facility was again the very similar site called Orca in 2021 with 4,000 tons of CO2 that were being captured in a year. Then on the right-hand side, you can actually see, along with DAC, director capture, we performed similar scale-up for point source capture and injection of CO2 and hydrogen sulfide from the emissions of the geothermal power plant that is nearby. And here you can see the scale-up of the different scrubbing towers from 2012 with a pilot, and then with Silverstone that was commissioned last year, being able to capture more than 95% of the CO2 emitted from the geothermal power plant itself. So that's like a major thing. Now, overall, just to show numbers, because we all like to see some numbers overall, since 2014, where Carbfix has scaled up commercially, within Iceland, we have injected more than 122,000 tons of CO2 underground. And I would also like to share with you a big milestone from last year, which I would like to highlight. This is like the Carbfix secured Europe's first storage permit for onshore geological storage of CO2, and this is like the very first permit ever issued for this onshore geological storage under the CCS directive. And currently, this permit allows us for 106,000 tons that can be injected annually, and overall this can be for 30 years, totaling to 3.2 million tons. So that's like a big step. Now, a little bit of a geological journey in Hellisheiði, where the site that everything basically began with a pilot in 2012. Now, on this slide, you can see Hellisheiði. This is a site in southwestern Iceland, approximately 30 kilometers east of Reykjavik, within this Hengil volcanic system. Now, the geothermal power plant, which is over here in the southern part, produces around 40,000 tons of CO2 and 16,000 tons of H2S like per year. And both these gases are just byproducts of geothermal energy, and they are of magmatic origin. Now, this subsurface, as we can see here, cross-section of a geological model, is dominated by quite young basaltic flows, shown here in blue, and lots of hyalopastite formations shown here in orange. Now, pilot operations began in 2012 with the injection of 240 tons of CO2 at approximately 500 meters depth, and this is like the temperature of the fluid at depth. And overall mineralization was not just inferred indirectly, but it was directly verified using geochemical analysis of subsurface fluids. Now, great, we talked about heterosiding. Now, if we just zoom out a little bit to the Iceland scale, we can see the potential for CO2 mineralization is a lot bigger, as 90% of Iceland is made of basalt. And now, if we just look at the young and most porous part of Iceland, which is within the active reef zone here as red color, the potential is between 950 and 2,500 gigatons of CO2. And basically what I want to show you with that is that the bottleneck of CO2 capture and storage is in fact not storage space, but other factors such as CO2 supply and initiatives. Now again, if we think beyond Iceland, which is zooming out a little bit more, we have favorable rocks that are widespread in every continent. Now you can see this mineral atlas. This can be, of course, accessible in our website. You can see these different yellow polygons on this map. These are all publicly available database that can show rocks that may be feasible for CO2 mineralization. Now the storage potential has been estimated in the hundreds of thousands of gigatons of CO2, which is much larger than we will ever need. So overall, the keynote message from me, and of course from Carbfix, is that we need more field demonstrations, and that's why I'm quite excited that I see these different efforts from all around the world. More pilot projects are needed to provide lessons from different sites, scales, so we can allow us to assess potential uncertainties and reduce risks. And this is exactly what Carbfix is trying to facilitate. And I want to show you just a few examples here in the following slides, and I'll be quite fast. One example is Helguvík site, which is very close to the airport in the Reykjanes Peninsula over here, and the seawater pilot called Seastone. This is the first pilot with injection of CO2 dissolved in seawater, because it's been mentioned quite a lot. Water is scarce in many places around the globe, so we want to understand if we can use seawater. And soon enough, our results from this pilot will be published. So that's a very exciting project to actually see it being materialized. Another big project that we are working within Carbfix, and it is actually the largest project that we want to develop in Iceland, is called Coda Terminal. This is a recipient of EU's Innovation Fund, a grant of 115 million euros, and the expected capacity is to mineralize 3 million tons of CO2 annually. And you can see here, this is like a rendering of our design. And I would like actually to show now another example on the other side of the world, which is looking at different rock types. Ultramafic rocks, we love ultramafic rocks, have been extensively studied because they are very rich in magnesium, and they contain a lot of reacting minerals like serpentinite, brucite, albine, etc. Now, one study, a colleague of mine, Katrin, she has actually looked at the potential in British Columbia extensively. You can read her research online. Many serpentinized ultramafic formations occur over there. So overall, when we have higher contact extent of serpentinization, rocks get more fractured, and we like fractures because we can have more permeability. And overall, when we have more brucite, then we have higher reactivity. So yep, ultramafic and highly serpentinized rocks are very good targets for CO2 mineral storage. And last slide, well, this is just one slide, basically just squeezing a lot all the efforts of MRV that being put into within Carbfix. You can see we're doing a lot of efforts, including major and trace element concentration, natural and isotopic tracers, CO2, soil flux measurements, and a lot of reservoir modeling. Of course, dissolved and mineralized CO2 cannot be detected by any kind of geophysical means, so that's why we need to use different types of chemical and isotopic traces. And I would like to show you here on the right-hand side, this is just a pump that was recovered, and you can see here the CO2 has been mineralized, and well, we were wondering what's the origin of that. Then we did a lot of calculations, and basically we figured out that the CO2 that was spiked in this calcite, it was spiked with carbon-14, so it was part of a tracer. So that's what's actually very cool to see on a pump itself. And yeah, I would like to thank you very much. And this is just the last slide with a couple of pictures of different operations. Thank you.
Excellent. Thank you very much, Angeliki. Remembering questions we'll do in the panel at the end. And just speaking on behalf of Australia as co-lead of both CDR and NIM mission, I'm sure that your map could extend to the right and show Australia as well. I'm sure it does. Thank you again. Our next speaker, moving along quickly, please, is Dr. Kun Tian, CEO and co-founder of Mesoscale Engineering Halcyon SRL, or MEH. Kun is a former practicing dentist turned expert in remineralisation biomaterials.
You see my screen?
We can. Just doing your introduction, Kun, it's fine.
Sorry.
Cementitious systems and structural alloys. Through her companies MEH in both Italy and Canada, she develops CCU technologies for diverse operating environments, producing profitable low-carbon solutions for infrastructure, agriculture, and industrial applications. Presentation is working fine, so I'll hand over to you, Kun, please.
Thank you, Alan, for the introduction. Thank NIM for the invitation. My name is Kun, joining you from our workshop in Central Rome, Italy. I am the CEO and co-founder of My Italy and My Canada. I'll start the timer. First, I would like to thank the previous speakers. Thanks, Sophia, for setting the stage for the CCU market, and Professor Hossein to introducing the background, highlighting its natural process we're reproducing in a controlled environment. And thank Angelica. It's very inspiring to see the large-scale deployment of CCU technology, and very inspiring.
Tian, I think you went on mute.
How about now?
Yes, better.
Okay, I'll restart. Here's an overview of our operation at this power plant in Calgary, Alberta, Canada, which supplies half of our urban and industrial energy needs. Daily output up to 50 ton flue gas, 60 ton captured CO2, also methane emission. Quick overview of our technology, mimicking aqueous-based CO2 mineralization, inspired by the nature, and the ocean is natural carbon sink, and there's carbonate sediments. And we're developing this flux-tolerant mineral carbonation technology via the GSD method. Get stuff done. And when I speak about the flux, is the flux of the CO2 purity in the flue gas, also the brine flux, composition flux. And also taking advantage of a spontaneous reaction, we're using ambient temperature and pressure. For example, in Alberta local temperature swing, this week alone, it's up to 27 Celsius temperature swing, and also seasonal flux. In the winter months, up to 40 Celsius temperature swing. Even in the summer, 30 Celsius, and which is the temperature swing is advantageous to our process, because when it's cold, CO2 dissolution rate increases. Also, the carbonate precipitation rate increases. When it's warm, the reaction kinetics accelerates too. How it works, where it all goes. More detailed look into our operation here. Daily, we have locally sourced brine, sediment basin brine, concentrated brine coming in. We regularly have a B tanker bring brines, and this shaded area is our bay, and the green shaded area is our shed in front of the carbon capture unit. Inside is our units, clear. We can see what's going on inside, no black box. And our logo, our slogan is we provide clear solution to climate. We have digital link, real-time process readout. And currently, at our capacity, we can simultaneously sequester and convert up to 6 tons captured CO2 using brine up to 36 metric ton per day and output 14 ton carbonate slurries. I would like to focus on this small unit, 120-liter linker unit. It's digitally mirrored to the unit in our workshop in Central Rome here. The same unit where I access the process to inform the process in Calgary. And also more, we have a desalination unit, output desalination brine as our feedstock. We have brine, a processed brine, and the product output to concrete blocks. And also we have dry form these carbonate blocks. We also have this 10-liter unit, travel unit, which fits into the discount airline carry-on, which I can take with me to my partners in different countries, in the UK, in Greece, to test the robustness of our technologies. We can use the flue gas from different sectors, cement, steel, energy sectors. And through these XRD, we can confirm the identity of our carbonates. And the workshop, the dimension to fit inside a 20-foot container. So it's modular solution. Output slurries in our recycling tank, targeting other produced waters. We managed to dewater the material fine tailings from oil sands operation. Where it all goes. Between year 21-26, we've upscaled 1,000-fold, and following this trend, predicted upscale potential up to 2030 is more than 12 kiloton. Our two major clients, this company, they are spraying our slurries for application as road stabilization and dust control. And the other company, where they produce carbon reinforced polymer, they incorporating our carbonates in their formulation to output into producing industrial process skids. I thought I would be at 6-7 minutes, which I'm at. A little bit pathway to today, a little bit history, in case I'm running out of time, acknowledgements of these entities supporting us, and the foundations. And back in 21-22, where I built these small units and observed different conditions, gives different products. We can control the particle sizes. And this led to me leading consortium securing funding from CETP. We managed to get everybody to the workshops in Rome, and I'm very happy to participate in CETP knowledge sharing workshops and also panel discussions, CCUS panel discussions. Scaling up from 8 to 12 liter, optimized unit dimensions and shape, taking advantage of the surface area volume ratio, taking advantage of fluid dynamics. We add different salts, different solution additives to accelerate the reaction kinetics, mimicking natural mineralization. We have carbonate lattice forming. We also control the output carbonate and particle size for different applications. Taking our technology into real operating environments. In Sicily, the salt production byproduct is a salt brine as our feedstock. Our dried form carbonates using in construction, also stable for storage, also wet slurry for application. And at this local alone, we can sequester and stabilize, fix, and up to 3.5 kiloton of CO2 per year. This is the lowest estimate. And also the financial gain, profitable. And as a proficient neutron scattering technology user, we had this vehicle to really have an atomic eye to probe the reaction technology, kinetics inside this in situ reactor. And we managed to track this time-resolved reaction to confirm accelerated kinetics and the yield. And this is a bit complex. This is array of our carbonates, different identities. But let me focus on this. It's all formed at ambient temperature, ambient pressure, because we want to achieve low energy consumption technology and different carbonate, different CO2 fraction, output density. And my acknowledgement. Alan, I see you. I think my time is out.
I'm not that harsh with my timing. If you'd like to make any closing words, please do.
Yeah, it's inspiring to join this panel discussion webinars to discuss the technology and then also upskilling environment of our peers. It's inspiring. I'm very happy to join this, and I'll leave it to you, Alan.
We're very pleased to have you, and I'm sure there'll be some interesting questions when we get to the panel at the end. Some accolades coming through on the emojis there. Our final speaker before we get to our panel discussion, but certainly not our least speaker, is Professor Tao Wang from Zhejiang University. Professor Wang holds a PhD in engineering thermophysics from Zhejiang and has completed a postdoctoral research at Columbia University in the USA. His research focuses on post-combustion CO2 capture and mineralization for co-producing bulk concrete materials from multi-sourced solid wastes. It's my pleasure to introduce you to Professor Tao Wang. Professor Wang, we can't hear you.
Hello? Hello? No?
It's very soft, Professor Wang.
You can hear me, right?
Yes, now we can, yes.
Oh, okay. Give me a second. I'm sharing the slides.
Thank you, sir.
Yeah. It's weird.
While Professor Wang's sharing his slides, remember, please put your questions in the end. We'll get to as many of them as we can. And those we can't get to in our timing today, we will hope to endeavour to answer and be able to provide to all registered participants of the talk. But over to you, Professor.
Can you see it?
Yes, sir. Please continue.
Okay. Great. I'm Tao from Zhejiang University. It's my pleasure to share into discussion with the experts in the audience. As mentioned by the previous expert, the CO2 mineralization primarily relies on the natural mineral resource rich in calcium and magnesium, or industrial solid waste. China's rapid industrialization and urbanization actually generate a massive amount of industrial and construction solid waste from the steel and cement and coal-based power plant industries. These wastes are rich in reactive calcium and magnesium components and possesses high specific surface area, making them excellent carbon sequestration medium. For instance, China produced about 500 to 600 million tons of flash and 400 to 500 million tons of slag annually. These resources can fix actually about 200 to 300 million tons of CO2 per year. China has conducted over 20 years of research in CO2 mineralization, led by institutions such as the Sichuan University, Zhejiang University, and the Chinese Academy of Science. In the last 5 years, the large state-owned enterprise like Bottle Steel, National Energy Group, and China Coal Technology and Engineering Group have also investigated heavily on this technology. Yeah. Over the past decade, several technical rules for products like fine calcium carbonate and concrete blocks have achieved breakthrough with breakthrough of the key indicators. The first route is direct flue gas mineralization using industrial solid slurry. This technology utilizes alkaline slurries discharged from the industrial processes, such as desulfurization slag and calcium carbate slag, to mineralize and fix carbon dioxide directly from the flue gas. I'd like to specifically highlight 15,000 ton per year industrial mineralization demonstration completed in Sichuan in 2021. In this project, the calcium-rich gypsum raw material from the dry desulfurization was prepared into a slurry and underwent current mineralization reaction with the CO2 from the steel flue gas within a large-scale vertical spray tower. And the project actually employed the mechanical surface renew technology for particles, ensuring high reactivity of the raw material and a high CO2 capture rate from the flue gas. By reacting the CO2 and gypsum sourced from the same industrial process on-site, the net CO2 mineralization sequestration rate reached over 70%. The second route is CO2 curing technology for the precast concrete. This technology perfectly integrates with traditional concrete raw material system and production lines. I'd like to share 300,000 cubic meter per year aerated concrete, the full production line mineralization retrofit project completed by my team in Zhejiang University in 2024. In this project, the CO2 from power plants and the fly ash and mineralization reaction within the same is a horizontal reactor. The project produced a porous thermal insulation wall material widely used in energy-saving buildings. It utilized AI technology to rapidly and in real time optimize raw material formula for the industrial solid waste from different emission sources. And simultaneously, a flue gas carbon capture unit was constructed to provide the high pressure CO2 required for the curing process. And this technology has a product's life cycle emission reduction about 120 kilogram of CO2 per cubic meter of the product. And this production line are operating continuously. The third route is a liquid phase mineralization of the steel slag. This route extracted the metals like iron and titanium while producing the nano calcium carbonate. The Bottle Steel's 20,000 ton per year CO2 demonstration achieves a negative emission of over 100 kilograms CO2 per ton of the products. And fourth technology is the CO2 mineralization in the ready-mixed concrete. And actually, this technology produced used in China and not only applied in the construction concrete, but the China Coal Technology and Engineering Group has also completed 100,000 ton demonstration project for mineralizing CO2 in the coal mine grouting and fireproofing material. Within large-scale bubble column reactors, the carbon sequestration rate of the flash slurry can reach about 5 to 7%, achieving the on-site consumption, the backfilling, and the utilizing of both CO2 and industrial solid waste. As the technical demonstration continued to progress, the early commercialization opportunity for CO2 mineralization technology have begun to emerge in China. Approximately a dozen startups have incubated from the research institute with their commercial strategies primarily centered around the three major scenarios: the green building materials, the chemicals, and the ecological restoration. For example, the clean CO2 spin-off from the Zhejiang University helped obtain the first domestic carbon footprint certificates for the solid bricks and ready-mixed concrete. Their lightweight concrete products are currently being shipped to a 480-meter super high-rise project in Shanghai. Another startup, the Green Ore, headquartered in Shanghai, led the steel slag CO2 mineralization demonstration with a capacity of 20,000 tons of CO2 per year at bottle steel and iron. And to encourage industrial decarbonization, the Chinese authorities are advancing the CCUS methodologies and standards. And also, the National Standardization Administration has established specialized committees to support the CO2 mineralization standardization. And furthermore, the sustainability goals of enterprise and social organizations have become a powerful catalyst in China. Tencent's Carbon X program has funded hundreds of millions of RMB into CCUS, with the mineralization projects accounting for 1/4 of the total. International collaboration with SDG responsibilities such as Hang Lung Properties, McDonald's, and Capital Land are also actively driving the deployment of this technology in China. Addressing the climate changes, collective emissions, China's practice in CO2 mineralization not only support the dual carbon goals, but also provide a reference for the other developing nations. So we are eager to deepen collaboration with the world in R&D standards and investment to contribute to the global climate governance. And thanks for your attention.
Thank you very much, Professor Wang, and beautiful keeping to time. That was almost perfect.
Yeah.
If I could invite all of our speakers to turn their cameras on now, please, we'll start the Q&A panel. To kick us off, I see Sophia's already got her camera on, so I'll hit you with the first question, please, Sophia. In your opinion, which countries in the world are leading when it comes to climate policy supporting mineralisation?
Thanks very much, Alan. Firstly, there is a lack of policy collaboration across the world. So firstly, it's really difficult to point to where the leaders are, because I think that there's not one leader that we can point towards, in my opinion. Be interested in the rest of the panel's insights. We do have the IPCC developing the methodologies at the moment that will be published in 2027 on CDR, CCU, and CCS. And so I expect once that happens, there'll be a significant rollout of methodologies around the world. I do see Australia as being one of the leaders to develop a CCS and CCU methodology for ACCU methodologies, and then we do see Japan as having quite a lead in this space, and Europe. So I'll pass to probably some of our other panelists to see if there are any keen insights there.
We possibly won't get everyone to answer the same question, Sophia, because we
Sure.
actually have a lot of questions to run
Oh,
through.
okay, sure. No
We've been
problem.
flooded in the chat with questions, so we might just limit each question to one speaker. But if there are opinions that anyone would like to put, please respond to them in the chat, and it will be captured for everyone to see. My second question coming through, I'm going to ask to Professor Hotite. Hussein, did you observe any decline in the injectivity over the injection period for the technology?
The short answer, we didn't actually, and this is something, some of the concern that many people think that, as mineralization occurs underground, it is volume positive. So meaning that when you put CO2 that is getting in its aqueous phase, CO2 interacting with the cations is going to form solid, and then eventually, right, is going to clog the formation and so on. But what we typically observe, and I believe this is in line with other experiences around, the other pilots, for example, and publications in literature, is that near wellbore, because you're actually in the acidic formation, essentially because you're putting CO2 and you have low pH. So essentially you are in the dissolution phase, okay, where you're dissolving, the cations out of the rock. So typically over time we experience the other way around. We experience improvement in injectivity, okay, over time. Of course, the volume positive will eventually happen, and mineralization will happen eventually, but typically happens away from the wellbore, where when you start, for example, the clog, maybe some of these fractures and so on, they would not impact the injectivity, because water will find its way around, right, to get in and go through other fractures and so on. Thank you.
Excellent, thank you. Obviously, saturation has to happen at some point, but we haven't found that limit. A geology question, and this is close to my heart because I'm a geophysicist myself. So, Angeliki, what are those key geological criteria for safe and permanent CO2 storage?
Well, that's a big question. We always need to answer and look for more data to actually find more sites for, that can be feasible for CO2 mineralization purposes. And this is actually like a little bit of a follow-up. I was going over the questions on the chat, so possibly I'll just half answer or so into this. I'll try to. Now, overall, yes, sure, there's so many criteria that we need to look at to assess the feasibility of a site, but focusing on the geology itself, a lot of volume and like depth of that reservoir, it's necessary to understand what are the limits of that. Absolutely, porosity, permeability, any potential fraction networks, understand if there is like hydraulic conductivity in the reservoir itself, because as what was mentioned actually earlier from Professor Hussein is we need to understand what are the resident times of these fluids in the subsurface, because this is actually going to be a key result of how efficient the mineralization is in the subsurface. So porosity, permeability, fracture networks, of course, geochemical composition. We have mentioned all these different rock types that can be feasible, like mafic and ultramafic rocks. We need to understand the storage capacity of the reservoir. Of course, water availability and chemistry. As we mentioned, it is quite a bit of a critical resource. Of course, we are pretty blessed here in Iceland, but this is not the case, as we mentioned, in many other places in the world. And water chemistry, it can affect mineralization rates, because of course you have more ions when you have like seawater, as we do have in our pilot cases within Iceland. And then of course, on top of that, if we just don't think only the geological criteria, we have like logistical factors like accessibility, distance for any suitable markets, etc., etc. Another thing I would like to follow up on the question regarding the mineralization rates and what can affect. Of course, like I mentioned a couple of those things before, temperature can be one factor that can affect mineralization rates. It's not though a critical factor for Carbfix technology. It can be demonstrated in low temperatures, but it can be demonstrated in higher temperatures. However, we can have a cap when we're dealing with the seawater. When we're going to degrees of 150 degrees Celsius and above, then we can have some precipitation on anhydrite, which is definitely not a mineral that we would like to precipitate. So this is just few of the criteria factors that I have in mind. And I'll just put a pause on that for now. We can go on and on discussing about this.
No worries. Thanks, Angeliki. The next question I have come up on the thing is for Kuntian. Kun, we don't succeed when we just capture CO2 in regards to creating value. So what actually determines whether or not the captured CO2 becomes an asset, or an economically viable asset?
Thank you, Alan. I'm happy you asked this question because we are all considering the economic value of our technology, profitable technology. And the captured CO2 alone is not profit, it's not value. It actually costs money to store it underground, under the sea. And when we want to create a value, we need to convert the captured CO2 into something valuable that can fit into the existing market. And also we want to reduce the technology cost in terms of capture effort and how sustainable, how much energy consuming the technology is. So for our technology, for example, we use waste brine so that the feedstock cost is low, and also it's locally sourced. So we reduce the scope 1, 2, 3, all carbon emission within our system. And also want to talk about the system integration. If technology can be integrated into the existing infrastructure, that's viable. And also the market fit, like Sophia highlighted, the market fit is very important. If our products can be sold at which value. So that's through this integrated process is when we create value.
Excellent. Thank you for that, Kun. Professor Wang, a question for you, please. Obviously, the life cycle carbon reduction benefits of CO2 mineralisation are apparent and a huge priority for China. How can technology further reduce carbon emissions?
Yeah, that's a very good question, because we all hope the CO2 reduced by this technology can be calculated accurately and treated on the market. And actually, the emission reduction benefit of this technology mainly come from the two aspects. The one is the direct emission reduction through the CO2 fixation, and the other one is the indirect emission reduction through the raw material substitution. And so the additional carbon emission reduction could be achieved by enhancing the CO2 uptake rate. And due to the kinetic bottleneck of the product layer diffusion control, especially for the small particles during the mineralization process, the industrial solid waste activation technology, as the liquid phase demineralization technology developing in China and also in our group to increase the conversion rate of the effective calcium or magnesium in the raw material, which can be over 60%. And additionally, the cement content in the most concrete products is between 10% and 20%. So this will generate a large amount of indirect CO2 emission. Therefore, the emission reduction can be further reduced through the CO2 mineralization with more solid waste without the cement material, and the adoption of the low carbon or carbon negative raw material can replace the traditional cement usage and to reduce the indirect carbon emission for the products. Thank you.
Excellent. Thank you very much. We have about 3 or 4 minutes left in the schedule for questions, but I'd like to get one more from each of you, if I could, in this public forum. But could I ask you to try and keep your answers to 30 seconds, because they're going to be quick-fire questions. So starting with Sophia, what is the product that you'll be selling from your plant?
We're selling magnesium carbonate, calcium carbonate, and silica powders. So they are the key products. They're being placed into supplementary cementitious material applications for the silica. And for the carbonates, we're looking at paint, paper, plastics, and a myriad of other products too.
Consumables, excellent. Hussein, quick question for you. Do you think this technology is scalable enough to serve as a long-term final storage solution for large volumes of CO2?
Very good question. I think extremely important. Of course, as I mentioned, I think it becomes, we already have general consensus and proof that this technology does work. The key challenge is how you make it scalable, as you mentioned, and this is where we need, innovation actually in terms of the engineering side. Okay, for instance, how Basel's, I think Angelique mentioned this, important factors related, for example, to the Basel, the fracture system, for example, the pore space, porosity, permeability, and so on, that in some cases, in some location, this can be challenging to achieve economic, for example, injectivity. And this is where probably we need to have improvement in the technology to achieve, for example, enhanced injectivity, for example, or, for example, optimize the conditions for mineralization. So I think we still have room to improve and optimize. In terms of the scalability, I believe it is there for sure. It is, again, as I mentioned, it shows very, very good potential in many places. In some places could be easier and could be maybe more suitable than others. But I believe actually as we evolve more and more and we see more demonstration, we're learning more actually about this technology. And I believe at some point we're going to make it scalable. Thank you.
Excellent. Thank you. Again, quick fire question for you, Angelique. What controls the mineralization rate in your reservoirs?
Well, I kind of try to follow up on this question, like when we're talking about the different geological criteria, assessing the site. Well, of course, rock composition is one of the things I will repeat once again that of course we want to focus on, mafic and ultramafic rocks. Then of course porosity, permeability, fracture networks. They are not necessarily increasing any mineralization rate, but they do improve a lot in terms of optimizing the balancing injectivity and the residence times in the subsurface in the reservoir itself. Then of course water chemistry, as I also previously mentioned, it's a factor that we need to understand because of its ionic composition that also controls mineralization rates. But yeah, water chemistry, availability of these reactive minerals in the rock, permeability, even though it governs how effectively fluids can be in contact with a reactive surface, and all of those things, they can optimize how we can balance injectivity and follow up on injection strategies on the reservoir itself.
Thank you. I think I'm being a bit unfair. I'm obviously asking questions that are impossible to answer in 30 seconds, but I'll try again. Kun, a question for you quickly. What determines whether a CO2 mineralisation is adopted in existing industrial systems? What's that? What's the main factor or the primary factor in your opinion?
I aim for answering within 30 seconds. I would think it's integratability, how it integrates into the existing infrastructure. Like the modular solution, it's a viable solution. It's very flexible and adjustable. It also the energy consumption. We aim for low energy consumption and the sustainable sustainability, because our goal is to remove the CO2, reduce the CO2 emission. If our own process uses high energy and then emits the CO2, it defeats the purpose. So for example, the 3 lines we always say: sustainable, environmentally sustainable, financially viable, and technologically scalable. So it's, in terms of scaling, it's our imagination is the limit. We can build units as big as possible, using different shapes, taking advantage of fluid dynamics, temperature swings, lots of factors in play. And I don't think it's untappable. It's very probable, very possible. It's inspiring how large we are upscaling, how fast we're upscaling. And we're in this skit together, and we're discussing the viable, pathway to move forward.
Thank you, Kun. This is going to be the last question we get time for before we have a very quick wrap up. So for you, Professor Wang, there are limitations because of mass transfer, so mass transfer limitations. Is there an insight you could share on how this mass transfer limitation can be addressed or engineered around when scaling up the mineralisation processes?
You're on mute.
Yeah. Okay. We have abundance of solid waste actually. So we are trying to avoid the massive transportation between sites. So, and fortunately, China has a lot of emission source with CO2 emission source with a solid waste. So we're trying to combine them together, and then simultaneously we produce the concrete or other chemicals which can be utilized in local area. So I think maybe there's one important way for the CO2 mineralization business in China. Yeah.
Excellent. Thank you so much. And I'm afraid that is all the time we have available for questions. So if I could please thank you all, but invite back Urban Piker to come back and give a short closing summary to thank everyone for the presentations today. Urban.
Yes, thanks, Alan. Thanks for the opportunity to close today's webinars. And I would like to thank you as well for moderating us through today's webinar again in such a smooth and pleasant way. Thanks, Alan. Great. I was really amazed by the presentation. So thanks to all the speakers, and thank you for sharing your insights about the incredible work you're doing and sharing your input in today's discussion. And I would also like to thank you. I would like to thank the audience for your active participation and all your knowledgeable questions. It really made this webinar quite different. Let me offer a brief personal wrap-up of this really inspiring sessions. In one of our previous webinars, we already covered CCU and CCS, and we called that webinar Carbon Shift, Redefining Industry through CCUS. And I think today we have made the picture more complete. What is clear to me is dealing with CO2 requires a shift in our mindset as well. And what has been presented today underlines the importance of understanding the resource qualities of CO2 rather than treating it merely as industrial waste, and to transform CO2 into products and to use it in industrial applications. Thanks for all the very tangible projects that have been presented. Once again, technological innovation is key, and it has already proven in many ways how to significantly speed up natural mineralization process. There are really exciting projects that are currently underway in international consortia, and the potentials for CO2 mineralization and reservoirs worldwide are huge. I would like to thank for the short journey around the world, visiting all the pilots where removal is already happening: Saudi Arabia, Iceland, Canada, and China. Next time we will hopefully be able to at least virtually visit even more field demonstrations and pilots, and I think Ellen might provide some support for identifying sites in Australia. I think this would make us all happy to see Australia covered here as well. There are still plenty of projects and topics to nourish our curiosity, both in basic research, in engineering and innovation, and obviously in the development of business models. And what I've found encouraging is the scale and speed of developments in that area. So I really look forward to follow up on the next steps in the different projects that have been presented. On a more general note, what we used to say at the end of these webinars is that the road to net zero remains complex, and collaboration and shared knowledge, particularly for such a complex topic such as CO₂ mineralisation and carbon circularity, that remains essential to make it achievable. So we hope today's session has sparked some ideas. I'm sure it has sparked some ideas, at least on my side, and that today's webinar has further strengthened trust in the potential of the presented technologies. So thank you once again, and we look forward to continuing this important journey with you until next time. And thank you for joining, and goodbye for now from my side.
Thank you, Urban. I can see Sophia absolutely grinning there. It's national pride, a matter of national pride. The Myrtle demonstration plant is in Australia. So we got that one covered as well, everywhere around the world, but that international collaboration is key. Juho, I see you're on camera there. Would you like to say some final words or perhaps thank our speakers?
Yeah, thanks, Alan, and thanks really everybody. I mean, CVR, CCUS, CCU, they all form this whole of that we or a holistic area of carbon management. It's really fascinating. It has potential to solve issues, problems, money in many sectors, and also provide business opportunities. So that's really great. So thanks so much to all speakers. Wonderful to see the breadth and depth of the projects and the opportunity that exists there, and also the sort of commercially driven opportunities that Sophia, you've shown there, as well as Angeliki, so from MCI Carbon and Carbfix. So it's great to see these projects move ahead, and as government groups, I think we can continue to foster R&D and innovation through our work, foster pilots and then more projects as well. But then also I think turn our thinking more and more into creating those enabling frameworks and conditions for these projects to drive in large scale in the future, creating demand for reductions and removals, and providing incentive frameworks and such like. So I think to your question or your answer, Sophia, on who's leading in policy, I hope we're going to have more countries leading in policy going forward. So yeah, thanks all for your talks, and everybody out there for your interest. Thanks.
Okay, thank you both. It's now my duty to close this session, but I would like to let you all know that a recording of the presentations, in fact all of our webinars, are available both on our YouTube channel and our website, and the link for that has been put into the chat by Oksana, our communications manager. We'd like to invite you to stay tuned to find out. Our next presentation is going to be, I believe, in June, and the topic is going to be decarbonisation initiatives from Asia. So we'll be looking for a regional view this time rather than a technology view coming up. But on that, as said, questions we didn't get to, we will try to address and make them available after the session. I'm not sure how they do that, but I'm sure there's magic ways that we've managed to get those back to all registered participants. But again, a thank you to all of our speakers. It is one of the most diverse, intelligent and informative groups that we've ever had, and it's very impressive to see you. So thank you very much. Thank you to both Juho and Urban for the work done by both of your missions. Thank you to the back office team at Net Zero Industries Mission who actually put all this together at the Austrian Institute of Technology. And finally, a thank you to our entire audience. Without you, without the stakeholders that we're actually doing the work for, we wouldn't have a purpose. So we want to thank you for your attention, for your questions, your interest, and your own commitments to actually helping to decarbonise heavy industry. So on that, I'll draw this to a close. Have a good day, have a good night, have a good life, and we'll hopefully see you next time.